So we have to discuss nano materials. We have just introduced the nano materials. Actually, when we refresh what are nano materials, we know that if any material has a dimension 1 to 100 nanometer size in any one direction is normally called as nanomaterials. It can be nanoparticle, it can be nanotube, it can be nanowire, it can be anything, but one of its dimension should be in nano size, 1 to 100 nanometer size. So we cannot, as we have already discussed, we cannot easily differentiate nanomaterials as nanochemistry, nanophysics, or nanotechnology or anything. It is actually nanoscience and technology. Every scientists are involved in nanoscience and technology. So next topic we have to discuss is nanotechnology. Nanotechnology is nothing but it is a deliberate design for designing the material and then construct the material, characterize the material, and utilization of the functional structure. So we know that different nano materials have different functions. Depending on the nature of the material, depending on the shape of the material, it has different function. And device and system through the control of matter at the nanometer length dimension. So this is what actually the core of nanotechnology. Everything is there. When a chemist can synthesize something, physicists can think about the property of the material, and then technologists can think about what is the application of the material. And also depending on the application of the material, the nanomaterials can be synthesized and characterized by chemists or physicists. So it is an interdisciplinary research area. Every field, nano technology or nanomaterials or nanoscience and technology means every different branches of science and technology is involved in this area. So there are certain terms we have to be familiarized. One is the quantum size effect. So what happens if the material reduces it to nanoscale? So this is what it means. So certain terms, one is quantum structures. Quantum structures, it deals about the structure. Here particles are electronically comparable to atoms and molecules. So we are synthesizing the materials in the nanometer scale. So 1 nanometer means 10 hydrogen atoms. So here it can be electronically comparable to atoms and molecules. So when we take a piece of iron rod or any metal, so that is a bulk material, because several atoms or several particles are made that material, that is the bulk material. So we cannot get the property of nanomaterial from the bulk material. So here we are making the material almost very close to atoms and molecules. So that means its properties will be definitely different. At this quantum mechanical scale, the properties of the materials will become modified and they differ fundamentally from those of the corresponding bulk material. So this is what the point is. When the size reduces, definitely the material behave differently from its bulk material. The quantum mechanical nanostructures are referred to as quantum structures. So the quantum mechanical nanostructures, we have already discussed the nanostructures. These are all the quantum structures. Now we have to familiarize with another term, quantum size effect. So this is the property of the material, quantum size effect. And this effect arises mainly because of the size of the material reduced to nano. When the size of a material reduced to nanoscale, the energy band structure will be directly affected, and the energy levels, and it will become discrete. So this means that you have already studied the energy level diagram in spectroscopy. So you might have seen different energy levels possible in the energy level diagram. These different energy levels are possible when we go more deeper into the matter. That means when we go to the nanoscale, this effect is more prominent. So that means when we talk about a nanomaterial, the electrons are more bound. That means it will be under the influence of the nucleus. So there won't be much electrons, loosely bound electrons present in the nanomaterial. So these bound electrons, when we reduce the size of the material, these bound electrons will occupy in discrete energy levels. Okay. So next slide you will understand it more clearly. The weakest bound electrons of these quantum size nanoparticles or quantum structures occupy quantized energy levels with a size dependent spacing. Quantized energy levels. What it mean? As you know, we are getting the energy as small packets. So that means these small packets, exactly like it is of differentiated into different energy levels. So that means it is quantized, means it is discreted. And this kind of effect is called quantum confinement. It is nothing but quantum confinement. The word quantum confinement is very important when we talk about nanomaterials. The quantum confinement just means that when the size of the material reduced to the nano, the electronic effect is more prominent and the electronic structure is different from the bulk material, and the electrons are more bound to the nucleus. Because of this, it behaves differently. This is what the quantum confinement. The spacing of the electronic levels and the band gap increases with the decreasing particle size. So as you know, when we studied the metallic properties, you have heard about conductors, semiconductors, and insulators. This is just like a conducting material. The conduction band and valence band is available. So there won't be any band gap between the valence band and the conduction band. When we go to a semiconducting material, there will be a band gap. There is a gap between valence band and the conduction band. When we go to insulating materials, this gap is still increasing. And this effect we can see that when the material goes to, for example, a metallic material goes to nanomaterial, the band gap is increasing because of the size reduction. I'll show you how it comes. Here the energy level type of diagram is shown. So this is the bulk metal. Okay. So this is the conduction band, this is the valence band, and this is the conduction band. So there is no difference between, or there is no gap between the valence band and the conduction band. When we talk about the semiconducting material, so here the valence band and conduction band, a gap is existing. So this is the band gap. Okay. So here you need to give certain amount of energy for these electrons to move to the conduction band. Then only this material will be conductive. When we go to the nanoparticles, the band gap is increasing because of the size reduction. Or the metallic nanoparticle metal will become semiconducting in nature when you go to the nanoparticle size. And then when we talk about clusters, some of few number of nanoparticles, again that increases. Here the number is diminished as compared to the number of nanoparticles available here. And then again we go to the molecular level. Again, so here you can see two effects. One is the band gap increases, and also the valence band is getting discreted. The energy of this level is not the same of the energy of this level. Okay, so this is discreted, okay, or separated. That is what it means. And again here also it is discreted, and then when you come here it is discreted and more explicit. Okay, so this is what is called HOMO. HOMO means highest occupied molecular orbital. LUMO means lowest unoccupied molecular orbital. You might have studied this. And when we come to atom, this is the electrons are bound. Electrons are bound and it is moving under the influence of the nucleus. Okay, so this is it means. The result of the so-called quantum confinement is that in this situation, the material chosen does not exhibit bulk metallic behavior. It cannot exhibit bulk metallic behavior, and this is because most of the electrons are tightly bound or localized. Localized means it will be near to the nucleus, cannot go unlocalized. Okay, totally bound. This is referred to as quantum size effect, and it is evidenced by a dramatic change in the electronic and optical properties of the material. So this means that the bulk material, when reduced its size to the nanoscale, definitely it shows different electronic and optical properties and also magnetic properties. For example, a nanoscale wire or circuit component does not necessarily obey the Ohm's law. The conventional metallic metal is obeying the Ohm's law, or the bulk metal is obeying the Ohm's law, but when the nanometal, the metal reduced its size to nanoscale, will not obey the Ohm's law, or not necessary to obey Ohm's law. Next term is quantum dot. You might have heard, but you don't know exactly what it is. So quantum dot means it's a closely packed man-made semiconductor crystal. Closely packed man-made semiconductor crystal that can transport electrons. It has very good applications in semiconductor industry. Quantum dot comprised of hundreds or thousands of atoms. Hundreds or thousands of atoms, and whose size is in the order of a few nanometers to a few hundred nanometers. So quantum dot size can be more than 100 nanometer in size, because it is a closely packed man-made semiconductor crystal, and its size can be more than 100 nanometer too. In other words, quantum dots are very tiny particles of semiconductor nanoparticles. This point is important. It is a semiconductor nanoparticles. They are so small that their optical and electronic properties differ from those of larger particles. We have already discussed this point. Quantum dots are band gap tunable. So I told you, depending on the size, the band gap will be changed, or decrease in the size, band gap increases. So depending on the kind of applications we are looking for, we can adjust the band gap of the material. The optical properties of the quantum dots can be engineered by controlling their size. They are a central theme in nanotechnology. This slide is not shown in your textbook, but for your information. Small quantum dots, such as colloidal semiconductor nanocrystals, can be as small as 2 to 10 nanometers. Different nanometer sized quantum dots can be prepared, and corresponding to 10 to 50 atoms in diameter, and total 100 to 1 lakh atoms within the quantum dot volume. So different size of quantum dots can be prepared depending on the kind of applications you are looking for. This is what this point says. Okay. So next point is, the self-assembled quantum dots are typically between 10 to 100 nanometer. Don't bother about it. I just want to show you a blue light of wavelength 450 nanometer is passing through the quantum dot size of 2 to 6 nanometer in size. So when it is passing through this material, the 2 nanometer quantum dot material will emit nearly a green kind of light. 2.5 size increases, green, and then 3 kind of yellow tint is coming, 5 orange is coming, 6 red is coming. Okay. So the emitted light will get more higher wavelength side with increasing diameter of the quantum dots. Okay, next let us see what are the applications of quantum dots. Quantum dots have excellent fluorescent properties, are made use as fluorescent probes in biomolecular and cellular imaging. Actually, this means that in order to scan our body, they want to check any disease or any kind of tumor or any other change in alignment in the body and muscles and cells. They can use nanomaterials in the probe, scanning probe you will be knowing. Sometimes, they will put certain kind of sensors or scanning probes at the tip of the wire, and they are just inserted into our body, and they will come to know what are the defects or what are the illness, what are the problems inside our body. So for that purpose, because of the excellent fluorescent property of this material, can be used as a fluorescent probes in order to used for bicellular imaging. And due to their electronic properties, semiconductor quantum dots are being used as active materials in single electron transistors and are being integrated into computer chips. I'll tell you what it is. It is given here. Transistor is a semiconductor device used to amplify or switch electronic signals and electrical power. So this is actually used to amplify the electronic signals and electrical powers. Okay, and single electron transistor will give a precise control of the movement of the electrons in a device. So single electron transistor. So the materials are coming to very small size, then only we will have some control over the movement of the electrons. So this kind of devices are also possible to integrate in the computer chips. Next, I am just telling you for your information. Don't take it. It is not given in the syllabus, but for your information, quantum tunneling, an effect that exhibited by the nanomaterials when the size is reduces. For example, like when we talk about a bulk metal, okay, when we talk about a bulk metal, and if there is an insulation or an impedance means insulation, impedance. So it has to go to the hill and then come down. So it should get more energy, kinetic energy, to overcome the insulation right in front of us, and then only it has to go to the other side. But when the material reduced to the nano size, it will show the wave properties. It will make a tunnel, and then move through this tunnel. So no need to go to climb to the insulator and then come down. It will directly pass through the insulator. I'll show you another picture. The wave property of the nanomaterials. There is an impedance, insulation. It is going through the insulator. Look at it. Very beautiful picture. Okay. So this is a very particular property of the nanomaterial. When the material size reduces, it shows wave kind of properties that you have already studied with electrons. Okay. Next is classification of nanomaterials based on nanoscale dimensionality. So the nanomaterials can be classified into 0 dimension, 1 dimension, 2 dimension, and 3 dimension. So this depends on which dimension. If one dimension is not in the nanoscale, it will call 1 dimension. All dimensions are in the nanoscale, it is called 0 dimension, etc. This is what it means. So let us discuss it. According to Richard W. Siegel, nanostructured materials are classified as 0-dimensional, 1-dimensional, 2-dimensional, and 3-dimensional nanostructures. So this is a 3-dimension. It is a nanoparticle type of material. So when you look at this individual nanoparticle, its all dimensions are in the nanoscale. This is 1 dimension. We will discuss it in the next slide. 1 dimension is like nanowire or nanotube. So this is X. So here X, Y, and then Z. Okay, so its one dimension is not in the nanoscale. Okay, so it is called one dimension. Two dimension, its two dimensions are not in the nanoscale. This dimension is not in the nanoscale and this dimension is not in the nanoscale, but this dimension is in the nanoscale. Three dimension means no dimensions are in the nanoscale. That means aggregated materials will be there. So this dimension is not in the nanoscale, this dimension is not in the nanoscale, and this dimension is also not in the nanoscale. Okay, so let's discuss. This classification is based on the number of dimensions of a material which are outside the nanoscale. Zero dimensional material, all the dimensions are measured within the nanoscale. All the dimensions, so it is shown here. So this dimension is nanoscale, this is also nanoscale, and this is also nanometer scale. Normally zero dimensional nanomaterials are nanoparticles, as we have seen, the picture is shown here. Next is one dimensional nanomaterial. Only one dimension is outside the nanoscale. So examples are nanotubes, nanorod, and nanowire. So here you can see that when you look at this example, this dimension is not in the nanoscale, but this dimension is in the nanoscale and this dimension is in the nanoscale. So tube-like structure, rod-like structure, wire-type structures are not in the nano, are coming in the one-dimensional nanomaterial. And two-dimensional material, any two dimensions are outside the nanoscale, as we have already discussed. Here you can see that examples, graphene, monolayer, and nano coating. Nano sheet is coming in this category. Nano sheet, nano layer, and nano coating, etc. are also coming in this category. Here you can see that this dimension is not in the nanoscale, this dimension is also not in the nanoscale, and this dimension is coming in the nanoscale. Okay, when we talk about individual material. And next is three-dimensional nanomaterials. Nanomaterials that are not confined to the nanoscale in any dimension. Okay, and this class can contain bulk powder, dispersions of nanoparticles, boundless of nanowires, and the nanotubes as well as multi-nano layers. So here you can see that the nano may be nanotube. So mesoporous composite, yes, right. The porous material, this is actually a porous material, but the bulk material is outside the nanometer dimension. This is a composite material, and so this actual size, when we talk about it's a bulk material, it will be it will be more than nanometer scale in 3 dimensions. And three-dimensional electrodes, but it is composed of nanomaterials only, individual nanomaterials. Then we will make it as a bulk material.